Hello, folks. You're tuning in to How to Train Your Gluten, brought to you by the University of Chicago Materials Research Science and Engineering Center.
Wait, hold up a minute. Train your what? We've heard of training your muscles, your cat, and even your dragon. But shouldn't we draw the line at training inanimate objects? Well, scientists say no, and let me explain why material training isn't what you might think it is. When scientists talk about training a material, they're referring to applying a repeated protocol that's able to modify small-scale structures in that material. And by doing so, this will change the properties of the material as a whole, such as making it more elastic, or squishy, or foldable. But actually, training materials is something that we've been doing for millennia. Long before trainable materials showed up in our research labs, they could be found in kitchens across the globe in a form that we all know and love: bread. Now, what does making bread have to do with material training? Well, I tell you and I can show you. Let's do an experiment that you too can conduct in your very own kitchen. We're going to make bread. Bread is made from a few simple raw ingredients: flour, yeast, salt, water, and in this recipe we'll use some butter. Next, we mix all of these together. And if at this point you think you've gotten trapped into a video about making bread, you're wrong. This video is about science, and we just made a material. Bread dough is solid but soft and easily deformable. Scientists would categorize dough as a form of what we call soft matter. But to see what's so trainable about bread, we have to zoom in on its microscopic structure. Bread dough is made mostly from flour and water, and flour is made of starches and proteins called gluten. One of these proteins, called gluten, attracts to the water molecules in the dough, and when they meet, it unravels into a long curly strand. As these curly strands come into contact with one another, they bond together. This forms a network of glutenins throughout the dough. But this doesn't just happen on its own, and that's why bakers have a training protocol for developing these microscopic networks. It's called kneading. Kneading is the process of repetitively stretching and folding the dough in on itself. It looks something like this. For this experiment, I'm going to split our dough into 4 batches. To each of these, I'll apply a slightly different training protocol by kneading the dough for varying amounts of time. For the first dough, I'll skip kneading altogether. We'll put this one in a bowl, cover it, and leave it to prove. For the second dough, we'll knead for 5 minutes. For the third, 10 minutes. And for the last dough, 15 minutes. So let's get training. We'll let these proof for a few hours and then check on them again. The yeast has caused our dough to rise and more than double in size. Now we can reshape and prove these one more time, get them baked, and find the results of our training. The breads are out. And the first thing we notice is that the final height of the bread increases with kneading time. The most kneaded bread is about 3 centimeters taller than the unkneaded one. The shape is also much rounder. Let's cut in and see what we find. While all the breads look fabulous in this lighting, on closer inspection we see that there are some differences in the crumb. The unkneaded bread looks dense and has fewer bubbles. The 5-minute crumb is more porous, and the more kneaded breads appear to have more long, stretched fibers. Now it's time to put these breads to the test. A test of resilience, that is. Well, bread 1 seems totally unfazed by this. Bread 2, I'm seeing some mild sinkage. Wow, bread 3 is really sinking, but look at that elastic recovery for 3 and 4. Just beautiful. But this is only the beginning, folks. It's time for round 2. Oh, it hurts just watching this one. Look at that rippage in bread 1. Those dents aren't going away for bread 2 either. Bread 3 and 4 look to be recovering alright. Perhaps bread 4 is going home unscathed. Now that's strength and elasticity, folks. We're taking breads 1 and 4 head to head in this round. Looks like bread 1 just can't take the gravity. Should have trained more. Look at that perfect plank from bread 4. Okay, enough fun. Our experiment is complete. We took a material, we applied a repeated training protocol, and we saw that the more trained breads became increasingly strong and elastic. Materials really are trainable. And as for the most successful tasting and textured bread, my vote goes out for bread number 3. This one had a great flavor and just the right amount of softness. Thanks for watching!